So last week you learned how to think about the question, how many different ways can I put n things in order? So if I'm trying to find all the different orderings of 3 things, the answer is there's 3 factorial, and here's what they all are. And this was one of the homework problems. So if I'm trying to put these 3 things in order, you can think about it as a fundamental counting problem where you say, how many options do I have for the first thing? 3. How many options for the next thing? 2. How many options for the last thing? 1. So that's 3 factorial. Okay, but what if, so this is the answer because each of these 3 things is distinguishable. So if I was going to swap any 2 of them, I would actually get a different possibility that I'd want to count. So what happens when some of your things are not distinguishable? What if I've got moo, and I want to know how many different ways could I put these 3 things in an order? Let's start with the same list, but let's replace the B with an O. But I'm going to replace it with a red O so that we can tell which of the O's used to be the B. So here we go. I'm going to make the change now. All right. So you can see those same 6 possibilities now have actually turned into only 3 possibilities. Because if I swap the 2 O's, as I've done here, you can see that they actually spell the same word. The only reason you can tell they're different is because they use different colors. But if I'd said how many different ways to reorder M-O-O, then it would just look like moo, and you couldn't tell that anything was different. So what we're going to do is we're going to take the original 3 factorial orderings and we're going to divide it by 2 because each one of the orderings has 2 different orders that count as the same. So there you have it. 3 factorial is the total ways to put 3 things in order. 2 is the number of different orderings that are equivalent. So what if we were going to add another letter here? So think how would you calculate that using the same approach for a minute. Go ahead and jot something down. So we'd start off by saying, how many total different ways can I put 4 things in order? And the answer is 4 factorial. Let's go ahead and write them all out, but I'm going to use 3 different colors for the O's. Whew, that was a lot of work. Okay, so you feel free to pause the video and look and convince yourself that this covers all the possibilities. I wrote them in a special ordering, which you can tell. Like you can tell that each column, the M is in the same position. So here M is in the first position, second, third, fourth. And then the relative ordering of the O's is the same as you kind of go down the rows. Anyway, you can pause the video and convince yourself. So this is the 4 factorial different ways of ordering the 3 O's. But as you can see, for each position of the M, all the different ways of reordering the O's give you the same word. They're all equivalent. So how many ways are there to reorder 3 O's? 3 factorial. 1, 2, 3, 4, 5, 6. So you can see I have my total 4 factorial, but if I don't count the different orderings of the O's, it's like I have this entire number and I'm dividing it by 6. So that's sort of like saying, what if I take all the possibilities and I divide them into groups of size 6, and you can see that there are only 4 different groups of size 6. So this is identical to the last problem. You can see why. 4 factorial was how many total ways to reorder 4 objects, but then because I can swap any O with any other O, that gives me 3 factorial ways that would all be the same as each other. So I'm dividing by the total number of reorderings that are equivalent. So what about this? How many ways could I reorder homonome? Well, there's 1, 2, 3, 4, 5, 6 letters. So I'll start with all 6 factorial ways of reordering those. But I know that I could swap any of the 3 O's, and that wouldn't change anything. So there's 3 factorial ways I could swap the O's. I could also swap the 2 M's, or I couldn't. So that gives me an additional 2 different orderings that would be the same. So you can see how this general idea of dividing by the number of equivalent orderings will generalize to a lot of other situations.